Okay, in the last lecture, we have seen how to find the Fourier series expansion. Okay, we will see some more examples on the Fourier series now. Okay, so let's have some more examples on Fourier series. Okay, so let's go for the example. Find the Fourier series for f of x is equal to 3x square minus 6 pi x plus 2 pi square by 12 in 0 to pi with period 2 pi. So here this is the given function, and we want to find out the Fourier series for this function. So let's have that f of x is equal to 3x square minus 6 pi x plus 2 pi square on 12 be defined in 0 to 2 pi with period 2 pi. And hence we have L is equal to 2 pi. So L is equal to pi. Now this function we can see that it is not required to check whether it is even or odd. So we can say Fourier series for f of x is given as, okay, we can have the Fourier series as f of x is equal to a0 plus summation n running from 1 to infinity an cos of nx plus summation n running from 1 to infinity en sine of nx. Let this equation 1, and where we have a0 is 1 upon 2 pi 0 to 2 pi f of x dx, an is equal to 1 upon pi 0 to 2 pi f of x cos of nx dx, and we have en is equal to 1 upon pi 0 to 2 pi f of x sine of nx dx. So this is how we are able to write the formula, the Fourier series for the function f of x. Now we have to evaluate this one by one. So let us evaluate this one by one. So we consider a0 first, hence consider a0 is equal to 1 upon 2 pi integral 0 to 2 pi dx square minus 6 pi x plus 2 pi square by 12, and this is dx. So we can have this 12 out. So we can write 1 by 24 pi 0 to 2 pi dx square minus 6 pi x plus 2 pi square dx. So let us integrate this. We can have 1 upon 24 pi. We'll be having 3x cube by 3 minus 6 pi x square by 2 plus 2 pi x and 0 to 2. So it is 1 upon 24 pi. This is x cube minus, you can have, this is 3 pi x square plus 2 pi x 0 to 2 pi.
Sir, it is 2
Sir,
pi
it will be
square.
2 pi square x.
Yes, it will be 2 pi square. Correct. Okay. So this is going to be 2 pi square. Now let us apply the limit. So we can have 1 upon 24 pi. So you got here 2 pi cube minus 3 pi pi square plus 2 pi square into 2 pi, and is going to be 0. All this term is going to be 0. So that's why no need to write this as we put x is equal to 0. This term is 0. This term is 0 and this term is 0. So let us simplify this. 1 upon 24 pi. So it is 8 pi cube. Then this will be 12 pi cube. So you have 2 pi bracket square, that will be 4 pi square into 3 pi. So it will be 12 pi cube. And then this will be again, you have, this is plus 4 pi cube. So this is going to be 0. So we can have 4 pi cube plus 8 pi cube, 12 pi cube minus 12 pi cube. So it will be 0, and hence we obtain here a0 equal to 0. So let this equation. Okay. Now we have to consider an. So let us consider an. So we have an is equal to, so we got the value of a0. Now we'll try to find out the value of an. So let us try to find out value of an. So what an we have, this is 1 upon pi 0 to 2 pi px square minus 6 pi x plus 2 pi square by 12 into cos of nx dx. Okay, so this is equal to 1 upon 12 pi. This 12 I am able to take it out. So we'll be having 0 to 2 pi 3x square minus 6 pi x plus 2 pi square and cos of nx px. So here we can use by parts rule. This is going to be u and this is going to be v. So let's have using centralize by parts rule v gain. So what we are able to get here is an is equal to 1 upon 12 pi. Now please be careful for the terms. Okay, so here we have this u as it is 3x square 6 pi x plus 2 pi square and the integral. So we'll be having sine of nx upon n minus the derivative of this term. So 6x minus 6 pi, and this will be minus cos of nx upon n square, and plus the derivative of this term will be having 6x and the integration of this. So minus sine of nx upon n cube, and here we'll be having 0 to. Okay, so now we have to apply the limits. So what we know is since sine
Sir,
of
in the last term, x will not come.
yes, okay, so you have 6. So since sine of 0 and sine of 2n pi is equal to 0, hence we get okay, an is equal to 1 upon 12 pi. So this minus and this minus will become plus. This both the terms will get cancelled or will be 0. So it is 6x minus 6 pi cos of nx on n square, and this is 0 to 2 pi. Okay, so let us apply the limits. So 1 upon 12 pi, and this is, you can have if I put x is equal to 2 pi, then this will become 12 pi minus 6 uh, pi. So that will become 6 pi and cos of n pi on n square. Minus, you are using lower limit, so this will become minus. This will become minus 6 pi because this term will be 0. And again we have cos of 0 on n square. Then since we know cos of 0 is equal to 1, cos of n pi is equal to 1. So we can write this as 1 upon 12 pi. This is 6 pi upon n square. This minus and this minus will become 6 pi upon n square. So it is 1 upon 12 pi, and this will become 12 pi upon n square. So 12 pi will get cancelled and we'll be having n 1 upon n square. So this is an, and hence we are able to write that an is equal to 1 upon n square. So let this next equation. So we got the value of a0, we got the value of an, and now we have to find the value of br. So we have an is equal to 1 upon pi integral 0 to 2 pi px square minus 6 pi x plus 2 pi square by 12 into sine of nx. Okay, so this is equal to what we'll get here 1 upon 12 pi. This 12 we can take out, and we'll be having integral 0 to 2 pi dx square minus 6 pi x plus 2 pi square and sine of nx. Okay, so this is going to be here. Now we can again use u into v rule. Okay, so we can use generalized by parts rule. So we'll have using generalized by parts rule, we get Dn is equal to 1 upon 12 pi. So here is px square minus 6 pi x plus 2 pi square remains as it is, and the integration minus cos of nx upon n minus the derivative of this term. So 6x minus 6 pi, and the integration of this term minus sine of nx upon n square. Now plus the derivative of this term 6 and the integration of this. So cos of nx upon n cube, and this is 0 to 2. Now before we apply the limit, so what we know is, since sine of 0 and sine of n pi is equal to 0, hence we have En is equal to 1 upon 12 pi. I can say this is minus px square minus 6 pi x plus 2 pi square cos of nx on n plus 6 cos of nx on n cube and 0 to 2. So what we get here, if we apply the limits 1 upon 12 pi, apply this limit. So if I apply 2 pi minus, so this is going to be 12 pi square minus 12 pi square plus 2 pi square and cos of 2n pi upon n plus 6 cos of 2n pi upon n. And this is, we are using lower limit, so minus minus plus. This term is 0, this term is 0. So 2 pi square cos of 0 upon n and minus 6 cos of 0 upon n cube. Now let us see what we'll get. So Bn is equal to 1 upon 12 pi. So this term is going to be minus So now you are able to see, correct? You are able to hear my voice.
Yes, sir.
Yes, sir.
Okay. So what we have done, uh, we have seen this step. Okay. So here, what we know is since cos of 0 is equal to 1 and cos of n pi is equal to 1. So this term is going to be 1. This term is going to be 1. This is going to be 1 and this is going to be 1. So we get this. And now let us see. This term will get cancelled with this term. This term will get cancelled with this term, and we are able to get the answer 0. So we get here Vn is equal to 0. So our equation 4. Okay. And as we know, we have calculated Vn, we have calculated An, we have calculated A0. So we are able to write the Fourier series, and hence we have from equation 1, 2, 3, and 4, we get f of x is equal to, so it is summation, then running from 1 to infinity, we have, then we have calculated 1 upon n square, and this is cos of, so we got here 3x square minus 6 pi x plus pi square by 12 equal to summation, then running from 1 to infinity 1 upon n square cos of, so this way we are able to get Fourier series of the given function in the interval 0 to 2. So we have any doubt in this example, you are able to get properly. So you don't have any doubt. That's good. Okay. So let's go for another example. Okay. Now we'll try one more example. So we have seen how we are able to find the Fourier series in the interval 0 to 2 pi. Let us see the Fourier series in the interval minus pi to pi. So we go with the example. Find the Fourier series for f of x is equal to minus pi less than or equal to x less than or equal to 0, and this is x going to be 0 less than or equal to x less than or equal to pi with period. So here the period is given to be 2 pi. So first we need to understand the function properly. So what is given, like f of x is equal to, this is minus pi less than or equal to x less than or equal to 0, and this is x 0 less than or equal to x less than or equal to pi. be defined in minus pi to pi with period. Okay, so we have VL is equal to pi, and hence L is equal to, okay. So now see, the interval is given minus pi to pi. So there is a chance that this function may be even or maybe odd. So what do you think, whether this function is going to be even or this function is going to be odd? What you can have, whether this will be even or whether this will be odd? How you are able to say that whether the function is going to be even or whether the function is going to be. So is it a even function or is it a odd function? You decide. So what happens when we want to decide whether it is a even function or whether it is odd function? Then we have to replace the term x by minus x. Okay. So let us see what happens if we replace the term x by minus x. So we have here, consider f of minus x. So if f of minus x turns out to be f of x, then it is even function. If f of minus x turns out to be minus f of x, then it is odd function. So when we consider f of minus x, that means wherever there is a x in the function, we have to replace that by minus x. So let us replace it. So we'll be having minus pi less than minus x less than equal to 0. This is minus x, 0 less than equal to minus x less than equal to pi. Now, to compare with this definition, we need to have x here. And so, how we are able to get x here? So, we know about inequalities. Okay. So, what we know about inequalities, if a is less than or equal to b, then minus b less than or equal to minus a. So that means if I multiply the inequality by minus, then inequality changes. Okay, so we have to multiply this inequality by minus 1 and this inequality by minus 1. If we multiply this inequalities by minus 1, we get f of minus x is equal to, so it is minus pi, 0 less than or equal to x less than or equal to pi, and it is minus x, minus pi less than or equal to x less than or equal to 0. So we rearrange this function. If we rearrange the function, that minus pi less than or equal to x less than or equal to 0, 0 less than or equal to x less than or equal to pi, then we get here this is going to be minus x and this is going to be minus pi. Now compare this function with the given function. So what we can see whether that function is going to be same. So you can check, here it is minus x, here it is minus pi, here it is minus pi, and here it is x. So this function is neither related to this is going to be f of minus x. So this f of minus x is nor neither related to f of x nor it is related to f of minus x, and hence this function is neither even nor odd case. Okay, so we know that if we have neither even nor odd case, then The Fourier series expansion of f of x is given as f of x is equal to a0 plus summation n running from 1 to infinity an cos of nx plus summation n running from 1 to infinity en sin of nx. That is equation 1. So we have where we got a0. Please be careful for the formula. So here we have the limit minus pi to pi f of x dx. An is equal to 1 upon pi minus pi to pi f of x cos of nx dx, and we have en is equal to 1 upon pi minus pi to pi f of x sin of nx dx. Okay, so we got here. Let us evaluate this one by one, and hence we consider a0 is equal to 1 upon 2 pi. So we have 0 as a point of discontinuity. So we have to split this integral into two parts, one from minus pi to 0 and other from 0 to pi f of x dx. Okay. Now let us integrate this. So we have 1 upon 2 pi minus pi to 0. The value is minus pi here and dx plus 0 to pi. The value is x and we have this x dx. So 1 upon 2 pi, we have the value minus pi x, and this will be minus pi to 0 plus x square by 2, and this is 0 to pi. So let us evaluate. This is equal to 1 upon 2 pi. If I put 0, this will be 0. Minus minus plus, you'll be having pi, and the value is going to be minus pi. So this for the first integral. For the second integral, it's going to be pi square by 2 minus 0. So let us simplify this. 1 upon pi, so it is minus pi square plus pi square by 2. So it is 1 upon 2 pi minus pi square by 2. So pi will get cancelled and you will be having minus pi by 4. So we got here a0 is equal to minus pi by 4. And that's what we have the second equation. Now, after finding a0, we have to think of an. So we have an is equal to 1 upon pi minus pi to 0 f of x cos of nx dx plus 0 to pi f of x cos of nx dx. So here we have cos of nx. Now what we have an. So 1 upon pi minus pi to 0. We have minus pi here, and this is cos of nx dx plus 0 to pi and x into cos of nx. Here you have to use u into v rule. This integral minus pi is going to be constant, so it is easy to integrate. Now using generalized pi parts we have. So what we'll have here, see the term an is equal to 1 upon pi. This integral will have minus pi sine of nx upon n, and this is minus pi to pi, plus this integral we have to be careful. X remains as it is, sine of nx upon n, minus the derivative of x is going to be 1, and this is minus cos of nx on n square, and this is 0. Now, since we know sine of 0, sine of n pi is equal to 0. So this term will vanish, this term will vanish. Hence, we have, so we'll have here an is equal to 1 upon pi. This minus minus will become plus. We'll be having cos of nx upon n square, and this is 0 to pi. So 1 upon pi, we will have cos of n pi upon n square minus cos of. Now, since we know cos of 0 is equal to 1 and cos of n pi equal to minus 1 raised to n. So, using this value, we get an is equal to 1 upon pi. This is minus 1 raised to n upon n square and 1 upon n square. So, this we can write as 1 upon pi minus 1 raised to n upon minus 1 raised to n minus 1 upon n square. So we get an is equal to minus 1 raised to n upon minus 1 n square pi. Okay. So this is going to be pi. Now here we need to be careful for one thing. So if we have minus 1 raised to n plus or minus 1, or 1 plus or minus 1 plus or minus 1 raised to n, then check for n p1, n p1, and okay. So we have to check what happens if n goes even and n goes odd. So here we have the case, and hence we have to consider if n is even, then minus 1 raised to n is equal to 1, and so we get an is equal to 0. If n is odd, then minus 1 raised to n is equal to minus 1, and an is equal to, so this time is going to be minus 1, minus 1, minus 1, minus 2. We'll be having minus 2 on n square power. Okay, so this is going to be the next equation. Now we have to check what happens to Bn. So now we have Bn is equal to 1 upon pi integral minus pi to 0 minus pi sine of nx dx plus integral 0 to pi, and here we have x into sine of nx. So here we have to use u into v rule. This integral is okay. So we can say using centralized by parts rule, we get Vn is equal to 1 upon pi. Then we have here is minus pi, and the integration is going to be minus cos of nx on n, and the integral limits are minus pi to 0. So here we have this. Now we have to think of next integral. So plus you have to use u into v rule for this. So x remains as it is, minus cos of nx upon n, minus the derivative of x is going to be 1, and here we have this is minus sine of nx upon n square, and the limit are 0. Okay. Now what we know is, since sine of 0, sine of n pi, that is 0, and hence we have, so what will get Bn? Bn is equal to 1 upon pi. We have this minus minus will become plus. So pi cos of nx on n. This is minus pi to 0 plus. It's going to be minus x cos of n pi on n. The limit is 0 to,
So it is nx.
yeah. So this is going to be nx. So we got here nx. And now we apply the limit. So 1 upon pi. So if I apply 0, then I'll be having pi cos of 0 on n minus pi cos of n pi upon n. Because if I put minus pi, this will become cos of minus n pi. But cos of minus theta is same as cos of theta, so we can write cos of n pi. So this is for the first integral. Now minus, I am taking this minus out. Okay, so if I use pi, so it will become pi cos of n pi upon n. And minus, if I use 0, this will become 0. So this way we are able to get the limits. Let us simplify. 1 upon pi, so it is pi upon n, minus this is pi into minus 1 raised to n upon n, and minus pi, this is minus 1 raised to n upon n. So what we know is, since cos of 0 is equal to 1 and cos of n pi, okay, so cos of n pi equal to minus 1 raised to n. Now simplify this. Okay, so you can have, so this is our Bn. So Bn is equal to 1 upon pi, pi n minus 2 pi minus 1 raised to n upon n. So we can have this pi common, and then we can write this as 1 minus 2 minus 1 raised to n upon n. So we got the value of bn. What by us 2 minus 1 raised to n upon n, and it's going to be our equation. Okay, so we got the value of a0, we got the value of an, and we got the value of bn. So using this value of a0, an, and bn in equation 1, we are able to write Fourier series for the one. So we can write here from equation 1, e, and we have. Please be careful while writing the Fourier series. So f of x is equal to minus pi by 4 minus 2 upon pi summation 1 upon n square cos of nx. But here this exists only if n is odd. So that's why we have to mention here that n is going to be odd. Now plus summation n running from infinity. This term exists for all n. So 1 minus 2 into minus 1 raised to n upon n. And here we have sine of. So this way we are able to find the Fourier series for this function in the interval minus pi to pi. So we have any doubt this two examples?
No, sir.
Okay,
No, sir.
good. So we don't have any doubt in both of these examples. And please mark your attendance before you give the class. Yeah, Mukul, what is your question, Mukul? Mukul, unmute yourself and you can ask the question. Do we need to simplify the odd summation? Uh, if okay, so if we require to prove the claim, then we need to simplify the series as all the odd terms. Okay, if we don't need to prove the claim, then it's okay to write the series in terms of summation. Is there any other doubt?